Hey, welcome everybody. Excuse me, this is Mr. Sheeline, and this is going to be for your chemistry class here, notes, Unit 3.1 notes, but this is part 1 of these notes, valence electrons and Lewis dot diagrams. So, before we get into all of this, just really make a note that this is part 1. So when we get here into Unit 3, there's going to be a lot of things that we're covering, and there's a lot of stuff to cover in like 3.1, 3.2, 3.3, and there's going to be a multiple number of notes. And so we're going to differentiate them with the parts, 1, 2, 3, however many that we need to have, because I don't want to give you a giant packet of stuff that you'll use for a week, but then you won't be using part of the packet for another week, so on and so on. So it's just better to do it this way, I guess. So that's just why we have part 1 now. And then specifically this part 1 is covering valence electrons and Lewis dot diagrams. Okay, so valence electrons. So valence electrons, these are the electrons as you should have read and maybe what you should have been able to see in that engagement activity yesterday after your test. Valence electrons are electrons on the outermost or the highest energy level of an atom. Okay, so what does that mean exactly? So remember, when we're looking at electrons, remember electrons are found on the outside of the nucleus of a particular atom. So if you have your nucleus here, okay, if that's your nucleus, remember you have all the electrons on the outside here. Okay, now what's different about this is that valence electrons specifically reference electrons that are found at different levels, we'll say, different levels, different rings, more or less, different energy levels, as they say here, outside of the nucleus. Okay, so now we don't get terribly into, in depth with this, at least for right now. All we want to focus on is really to focus on, super simple understanding of it, and that's just the super simple understanding that valence electrons, again, are just, they are found outside, and specifically it's the outermost that we care about. So for right now, all that we need to know is that there are a number of different levels, but we just want to look at maybe 2 or 3 of those levels. Now, real quick, the first level here will have the max you can have on the first level. The max number of electrons is 2. Okay, so for instance, helium. If you have a helium atom here, helium is all ready to go. It's got its outer valence shell all filled out. If you have hydrogen, hydrogen just has the 1 electron out there. So sometimes it'd be nice for it to have, to either give that up or to fill it out. Depends upon the reaction. But as another example, let's maybe skipping ahead just a smidgen, but just so you understand. Let's maybe look at oxygen. So oxygen, now we don't know that you don't know this yet, but I know this. Oxygen is going to have 6, or it's going to have not 6 but 4. Oh my goodness, my bad. They will have 6 valence electrons. Okay, now how do I know that? Well, if I look at oxygen on the periodic table. On the periodic table, its atomic number is 8, so that means it has 8 protons. So I should expect, if it's not an ion, I should expect that there are 8 electrons as well. So if this is my nucleus, remember the max that the first shell can hold is just 2. So there's 2. So I've got 2 electrons. Now the second ring out here, the max it can hold is 8. Okay. So the max, the highest number of electrons that the second shell, the second level can hold is 8 electrons. So if I'm still working with oxygen here, the first shell is all filled up. So now I've got the second shell, 8 minus 2, because that's all, or sorry, 2 minus, my goodness, 2 minus 8, that is 6. So 1, 2, 3, 4, 5, 6. Okay. So this is what we're talking about when we're talking about valence electrons. So we are, because that's all the electrons that oxygen has, we're focusing on this very outer shell. We're not worrying about the inner one, just the outer one. And here we would see that oxygen has 6 valence electrons. Okay. Now, you're probably wondering, well, why is it important to know that? Well, it's important to know that because we're going to be getting into how to, exactly how certain things bond or why certain things bond. So electrons are used in determining how an atom will bond, how they will react with another atom. So understanding and knowing how many valence electrons a particular atom has, the better. Okay, and actually it's necessary. Okay, so the number of valence electrons on an atom contains is equal to the family column number it is in. So now, because I already know that, and I just walked you through that, for, let's say, oxygen, you can, more or less see how many, why am I losing my train of thought here? You can see how many valence electrons you would have just, knowing that 2 will be on the first shell, and then you can have up to 8 on the second, and then seeing that there's 8 electrons, and 2 on the inside, 6 on the outside. Boom, I've got it. But then what this is referencing is that this is referencing a nice little thing that we can use on our periodic table. So if you were to get out your periodic table, what you would see is this. So they mentioned the family columns. So still using oxygen as an example here. So you notice oxygen has this family level 6A. And for the most part, this column here, that oxygen is in, the 6A, these elements have 6 valence electrons. Ooh, isn't that so nice? Isn't that so cool? So that means then in column 5A, nitrogen has 5 valence electrons, phosphorus has 5 valence electrons. Carbon is in 4A. So that means that carbon has 4 valence electrons. And I think you're starting to get the picture here. So it's using the periodic table, we can use the periodic table to quickly just reference and see how many valence electrons a particular element should have. Okay, which is super nice because then it makes our life a little easier, especially when we're doing practice problems like this. So as an example, chlorine being in 7A, chlorine will have 7 valence electrons. Okay. And then as the next problem, barium is in 2A. So barium will have 2 valence electrons. Okay. Now hopefully you see the picture here. So remember, if you've lost it already trying to remember what those valence electrons are, remember valence electrons are these guys. They're you have the nucleus, you have energy levels, different energy levels. The first energy level can hold 2, the second one can hold 8, and the next one can hold 8, and then 16, 64. There's a sequence to it. We won't get into it right now, but that's later down the road. But for the most part, it is this most outer shell that we care about, because the most outer shell is obviously, if you smack 2 atoms together, the outer shell is what's going to be interacting with another outer shell of another atom. Now there is one exception, and it is helium. So helium is it's in column 8A. Okay, as we can see here, here's helium. It is in AA. Why is it in AA, and why isn't it out here with beryllium? With beryllium and magnesium? More or less, it's because helium it follows some of the patterns. It has some characteristics similar to all of our noble gases here. And on top of that, it has its outer shell filled. It's ready to go. It doesn't need any. Because if you think about it, lithium over here, lithium is going to have 3 electrons. So there's 2 on the outside, 2 on the inside energy level, 1 on the outside energy level. So it's wanting maybe 7, or at least most likely giving up one of those electrons on the outer level. Beryllium here, 2 on the inside, 2 on the outside, okay, which is different from helium. Helium's all filled. It doesn't need any more. Its innermost shell has 2. That's all it can hold, and that's all it wants. So that's one reason why we put it over here as far as that's concerned on the periodic table. Okay, so now that we can for the most part, have a somewhat of a working idea of what valence electrons are. We can represent these valence electrons through what's called the Lewis dot diagram. And a Lewis dot diagram it's not only just to show the number of valence electrons a particular element has, it's a really nice representation of showing how different atoms will bond to one another using little dots. Okay, so more or less it's just a visual depiction of an atom and its valence electrons, and that's pretty much what I just said. So, excuse me, as an example, like the one up top, chlorine has 7 valence electrons, and we know that because it's in 7A. Chlorine here, it's in 7A column. So what do we do in showing a Lewis dot diagram with chlorine? Well, what we're going to do is we got to keep some conditions. We are going to show no more than 2 dots, and the dots are going to be our electrons per side. And we're going to try to keep, and not just so much try, we are going to keep electrons balanced around the symbol. Now, how do we do that? Well, let's just start off real quick on showing how we just do this. So when we're showing Lewis dot diagrams, we use the chemical symbols. So we'll put Cl. Now again, because we've got 7 valence electrons here, okay, we're going to start putting dots all around our chemical symbol, and this is what we should have seen in the engagement yesterday, just kind of glancing through either one of those links. And we're going to start placing dots all around Cl to represent the valence electrons. So I know that chlorine has 7 valence electrons, so I'm going to put 7 dots all around chlorine. Now, when I do 7 dots, this is how I do this, and this is how we keep it equal. Okay, I go like north, south, east, west kind of idea. Not so much in that order, but like I like to keep your y-axis here and your x-axis here on in reference to our chemical symbol. So like this, I'll put 1 dot up here, 1 dot down there, a dot over here. Okay, and you see how that's like equally distributed? That's what I'm looking for. And so, but obviously we're not done here yet. So then I'm going to double up here, double up there, and then there's our last one there, because then we can't hold any more on here, because that's, or not that we can't hold any more, it's just that's all that chlorine has. So this is what we're talking about, is that condition of keeping them balanced all around the chemical symbol. Here's what I don't want. So this is what do want here. This is what I don't want. This is what I don't want. Okay? To just make it super duper clear. This is what I do not want. We do not want to do this. Was that 1, 2, 3, 4, 5, 6, 7? No. Do not do this. Okay? Don't do that. Don't. Okay? The reason why we don't want to do this is because when we get into bonding different atoms with one another, we typically don't do this. We don't just shove the other atoms, whatever they happen to be. We don't just shove them randomly around our other atoms. We don't do that. They're nice and straight. They're at particular angles, and they have to conform, to a decent structure. Because if you don't, your reader's going to be confused, and you're going to be confused, and plus you're not accurately representing your bond. So when we make these, make sure keep them nice and even, okay, and just follow these 2 conditions. And then the one I didn't mention here, just 2 dots per side. So anyway, so if you want to think of it another way, think of this. If I wasn't clear on how to place your dots, think that there's a box around your chemical symbol, and each face here, each face of your box is a side, okay, and each side can hold no more than 2. Think of it in that way, okay. Now, as far as who gets the single dot, that's up to you. Like which face gets the single dot, that's up to you. It really doesn't matter as of right now. It does in the future, More specifically, when you get to Chem 2, it does, because then it really matters with the particular, when you get to isomers and other kind of things, it matters how your atoms are oriented and how your valence electrons are oriented. But anyway, we don't need to know that for now. So what we just need to know is just the simple basics. So let's try oxygen. Okay, so we know oxygen has 6 valence electrons because we know it's in 6A. So let's and I'm just writing that down to help you out some more, to remind you. So let's do this. So oxygen, okay, that's a chemical symbol, it's just O, has 6. So I'm just going to do this. I'm going to go 1, 2, 3, 4, okay, and then I'm going to do this 5, 6, and that's balanced and that's even. That's fine. Okay, I've got 2 up top, 2 below, 1 on each side, and that's okay. Another way you can do it is like this. You could do this. You could go 1, 2, 3, 4, 5, 6, and that's fine too. Okay, so that's also fine. I'm trying to think of if there would be a way to, in this case for oxygen, because it's an even number, there really isn't a way to mess it up, but there is for nitrogen. So let's do nitrogen. So nitrogen is in 5A. So nitrogen here. Okay, 1, 2, 3, 4, 5. Okay, looks nice. Okay, so nice and even. Now you can mess this up in depending how bad you messed this up. I might take points off, because here's, as far as what we're practicing now, I really don't want to see this. I don't want to see, I don't want to see this, because this it's not even, it's not balanced. There are some teachers and there are some professors at universities that are fine with this. I'm not, as far as teaching you guys, I don't want this. No. Do not do this. We want it nice and even, nice and balanced on all sides. It's fine if an electron's sitting all by itself. Okay, like up here, like these guys here. As long as it's nice and balanced, think of it in this way. If you can cut it in half and both sides are the same on, they're mirrored, it's all good. It's fine. Okay. So, and then the last thing in the notes here, the Octet Rule. So this is something that you should have ran across, what you should have answered, part of the engagement. The Octet Rule, hard and fast, is an atom. It's the rule that states that atoms tend to gain, lose, or share electrons in order to acquire a full set of valence electrons to become stable. And usually it's 8 electrons. Now that's not, it's not a rule that can be applied to every single atom across the periodic table, or element, I should say, across the periodic table. But for the most part, the stuff that the elements that we're going to be using and the types of bonds and chemicals and compounds we're going to be making, this will work. So what does the Octet Rule look like? Well, real quick, the Octet Rule looks like this. So let's see here. To use an example, to use a chemical, a compound you already know. Let's use, and actually I'll use the other side of this. Let's think about H2O. Okay, so H2O, just broken down, we have 2 hydrogen and 1 oxygen. Make that a 1 oxygen. Okay, that's not a 10. That's 1 oxygen. So if we break these down into their Lewis dot structures, then hydrogen's going to look like this. Okay, here's 1 hydrogen and here's another hydrogen here. Okay, and then oxygen is going to look like this. Okay, so the Octet Rule states that atoms tend to want to gain or lose, or sometimes even share the electrons in their valence shells. Now, the typical rule is that if you've got more, like so. Typically, from nitrogen over these 3 guys, these 3 columns, typically, they always want to gain electrons. Not always. It does depend upon the type of bond, but typically these guys want to gain electrons because they're closer to the rule, or they're closer to gaining all 8. And then these guys over here, lithium and beryllium especially, like these two columns here, these two columns all the way over here, they want to give up because they want to give up electrons because they want to, become stable, and they don't want to have extra valence electrons flying around because it'll be more difficult to fill in their valence electrons since, lithium has 1. That would mean it needs 7. What do you think is going to rule over, in this rule? Do you think it's going to be easier to get 7 electrons, or is it going to be easier to get rid of just 1 electron? It's going to be easier to get rid of 1 electron, okay? So hopefully you're already starting to see it. We can see here there's a spot where, potentially there's some room here to where, oxygen can bond with these two hydrogens, and this is getting a little ahead for what we're practicing, but this is what it looks like. Is like this: is that there's an empty space here. Oxygen would love to have 8 valence electrons. There are 2 hydrogen atoms with one electron on each of them in their valence shells. So that means that for the most part, hydrogen's probably going to want to kind of toss that electron towards the oxygen. So we would write it like this. Now this isn't perfectly accurate because water molecules are bent. We don't get into that just yet. That's getting into bond angles and orbitals, and we don't get into that just yet. But simply put, so here's 2. I'm going to move 1 down here, like this guy's going to be moved down here, this guy's going to be moved down here, and I'm going to change my color here just so you really can see it. So there's still 6 valence electrons, but here is where the hydrogen comes in. So here's the hydrogen, and it's bonding with more or less tossing its valence electrons here into the oxygen. If I were to show this a little bit more accurately, it would look like this. It would be oxygen 1, 2, 1, and then it would look more like this. Okay, but that's according to its bond angle, which again we don't get into yet, but same thing still applies for the most part. It's the idea of this. It's the idea that we can use the Lewis dot structure to show where these atoms will bond, where it is that they are willing to either share or not share, but to take electrons away. So that's the octet rule. That's how we use Lewis dot structure, in reference to the octet rule. This is, for the most part, a pretty good overview of valence electrons and why we care about them. And yeah, so those are the notes, guys. If you still have any questions, go ahead and ask away. If not, then I'll just see you in the next one.